I think it will be welcome bonnets to this session. Hello, are you hearing me?
Yes, yes, we can hear you. Please carry on.
So let's start with the session. In this session, we have three invited talks of 30 minutes each. And for the invited talks, we have a time schedule, time breakup of 25 minutes for the talk and 5 minutes for the question and answers. So we would like to be on time, and we start with the first talk by Michael Bonnet, and the title of his talk is Perspectives of Quantum Plasma and Dense Matter Theory. And Professor Bonnet is from the Kiel University in Germany, and he is an authority in quantum plasma, and he has written many books on the topic. And has his review article, which came last year, is of course a um, thing to cherish with, and all of us should have a look at that review article. So I would request Professor Bonnets to start his talk.
Thank you very much. Thank you, Punit, for these nice words, and thank you, Dr. Prajapati, for inviting me. I hope everybody here is making it well through this crazy pandemic, and I also hope that plasma physics will not suffer too much. So if you don't mind, I turn off my video in order to not suffer bandwidth. I wanted to turn off my video. I have to do it first. Okay, second try. The title of my talk was already mentioned. Here are my co-workers. Jandas was a postdoc, did his PhD in my group, and Tobias also. Paul is a new undergraduate student, and Jan Vorberger is a collaborator in Dresden. Downstairs, you can see a link to my webpage. The talk is available on my webpage. If you go to research and then talks, you can download it. There's a lot of material. I will have to skip in this talk some of the material, but you can read it. So what is warm dense matter? This is highly compressed matter, which is shown here in this picture. I hope you can see it. And I also hope you can see my mouse pointer here. So usually warm dense matter is at quite high temperatures around the Fermi temperature, which is written here. So we have a dimensionless parameter theta from 0.1 to 10. And the densities are also very high. The densities are shown here are typically on the order of solid density or even 1 or 2 orders of magnitude above this. So this is found in this core of dwarf stars, for example. This is also found on the path to inertial confinement fusion. So this is a very important and modern research area. The difficulty here is that from the theory side, this is a quite complex material. We have condensed matter, so we have atoms, we have solid substances, we have plasma phases, or they can coexist. And this is at quite high temperature, as I already said. So typically, from a theory side, it is not possible to apply perturbation theory or zero temperature theory. So you have to do something better. From the experimental side, it is also a quite challenging subject because at these highest densities, it is very difficult to get reliable measurements. But now for 5-6 years, we have very accurate measurements from light scattering. I will show some results a little bit later. So what can we do if perturbation theory does not work? Then one way is to first look at model systems. And here I will concentrate on the uniform electron gas. This is a difficult quantum component in this dense plasma system, which determines the properties. And this has been an important subject for many years, since the 1980s already. And the ground state properties, t equals 0, have been studied very well and very accurately with computer simulations, with quantum Monte Carlo. And these quantum Monte Carlo simulations computed the exchange correlation energy, which is the total energy minus the ideal energy. And this is the difficult part. The ideal energy is of course known. And this exchange correlation energy went as an input into density functional theory. And density functional theory is now the governing method for computing materials, atoms, molecules, and also warm dense matter. So there's no way around DFT, but DFT relies on accurate input for the exchange correlation energy, which is delivered by quantum Monte Carlo. This was ground state. Now I told you that we are at high temperatures around the Fermi temperature, which can be 10 electron volts or even more. And this is a challenge for density functional theory, but it's also a challenge for quantum Monte Carlo, because now we need to have as an input, not the exchange correlation energy, but the exchange correlation free energy, because we have entropic terms to take into account. And this exchange correlation free energy is an input for all kinds of models, equations of state models, but also for the density functionality, but also for all kinds of thermodynamic quantities. Via thermodynamic relations, you can compute all other quantities. That was the status, let's say, 10 years ago in computing the exchange correlation free energy. There were a lot of different models, which I list here. I will not read them for you. Here's the exchange correlation free energy density as a function of this temperature parameter. Remember that this is the Fermi temperature. Here we have quantum systems. Here we have classical systems. And you see at some density, which is around metallic densities, there's a lot, quite huge difference between these models. And it's not clear what model is correct or if any of those is correct. And the only answer can be given by simulations, by ab initio simulations. And this was what we did for the last 5 years. So we used the finite temperature quantum Monte Carlo version, which is based on Feynman's Path integral formulation. But this has a problem. This is related if you simulate fermions, which are half spin particles, which have an antisymmetric wave function. This antisymmetric wave function or antisymmetric density matrix, which you have to compute, has sign alternating terms in a sum. And this gives rise to severe numerical problems. You have a loss of accuracy if the quantum degeneracy, so quantum effects increase, the efficiency of simulations drops exponentially. And this is, of course, a disaster. And people have done different things. People have done approximations. One is this so-called fixed node approximation. This postulates that there's no sign problem. One does effectively a bosonic simulation where no such problems exist, but the errors are unknown. And also these simulations are restricted to quite low densities, RS larger than 1, which is shown here. So high density is now to the left. Here's the ideal Fermi gas when RS is 0. So this is a range where these simulations could be done. So we tried to avoid these uncontrolled approximations. We developed 2 new approximation schemes. One is configuration path integral Monte Carlo, which has no problem in computing the ideal Fermi gas. These are these vertical dashes where we can do the simulations. It's exact at small rs. And the second method, it's permutation blocking, path integral Monte Carlo. I will call it PB-PIMP here. It is shown by the horizontal dashes here. And you see we have a nice overlap over large portions of this warm dense matter regime. Here is a gap where we cannot do simulations at temperatures, say, below 1/2 of the Fermi temperature. But having these independent ab initio methods, we could do some simulations and verify earlier calculations. So the blue lines here for 2 temperatures as a function of this coupling parameter are these restricted path integral Monte Carlo simulations, and you see they stop here. And also they show some unexpected, let's say, behavior. Now we compare them to our configuration path integral Monte Carlo, which is good at high density. And you see these are the simulation points. You cannot hardly distinguish the error bars. Simulations are very accurate. And we can clearly see that these blue simulations are not correct. And but we stop here because the sign problem kills us here at these moderate couplings. But the other methods, this PBPIMP, which are these crosses, this works at low density, at large RS values. And you see that we have a nice overlap here at this temperature. At this temperature, we cannot do simulations here, but we still can interpolate here. So we get a complete picture of the thermodynamic properties without any approximation in this parameter range. So this is a limit which we can achieve, but we then continued this, compared this to ground state simulations, and could close the gap to the zero temperature also. So this is available in this review paper, which we wrote 2 years ago, and there you can check it. So the message is, for the electron gas, we can do all the thermodynamic properties practically exactly, and if anybody has a model or a simulation, another simulation approach, you can take these data as benchmark to test your model or improve your model. So these were static properties, thermodynamic equilibrium. Now I come to the second point, which I will devote the rest of the talk. This is dynamic properties. This means also in thermodynamic equilibrium, but frequency dependent properties. And what is an important quantity is this density correlation function, or this dynamic structure factor, which is the key in scattering experiments. Now on the right, I show a picture of such a scattering experiment. You come in with a laser with a wave number K0, this is the incoming. Here you have your plasma or warm dense matter or atoms, whatever. Light is scattered at these particles which move with a velocity v, and the scattered light has this wave number. So this K is a change of the wave number, which is by momentum conservation transferred to the particles. And what is measured in these experiments, which are typically done with X-rays at free electron laser facilities in Hamburg or at Stanford or at other machines, is this scattering signal. So you measure this peaked structure of the light scattering as a function of wavelength or of frequency. And from that, you can get insight into a very complicated warm dense matter system. So the area gives you an estimate of the density, and the width of the peak gives you an estimate of the temperature. But you can compute these plasma parameters only if you have a good model for the dynamic structure factor at hand. So here, modeling and theory is required as an input to understand experiments. So it is very crucial now to have good data for the dynamic structure factor, so for these frequency dependent quantities. And we have tried to do this with our Monte Carlo simulations. But it is difficult because here you get this density correlation function involves density fluctuations at a wave number q at different times, t or time t0, and then you do a Fourier transform. But in Monte Carlo, we do not have time. It is purely equilibrium. So you have to do an analytic continuation in order to get access to this quantity. But just in a second, I just want to mention that people are able to get models for this dynamic structure factor involving very different processes. There can be scattering of light at atoms, and this light, this photon absorption can excite atoms to higher levels, for example. So these are called bound transitions. There can be bound free transition where an atom is ionized, and there can be free transitions just involving free plasma state. So what we can do here is not the full, at the moment, dynamic structure factor, but we can get a good estimate for the free part, because this can be modeled by this electron gas model, which I have described before. And here is an experimental picture of this dynamic structure factors. These are the blue dots as a function of photon energy. And you see a very characteristic measurement. And you also see that the scatter of this point is surprisingly small. So you can get very accurate data indeed if you are able to interpret these data. And this is an important challenge for quantum plasma theory of the next years, I would say. Here I also plotted the different contributions, and the free is the yellow one, which we are trying to get access to. Okay, this is now what I mentioned. We have no time So what one can do is to go to imaginary times, which means we begin analytical continuation. I have no time to explain this in detail, but there is a clear procedure now by getting the dynamic structure factor. We can reconstruct vice versa this scattering amplitude. And this is what we do. We also include all kinds of information which we have, frequency moments, for example, of these quantities in order to get access to the dynamic structure factor. And I have to make this a little bit short, just to show you two examples. Here's a typical picture of the dynamic structure factor as a function of frequencies. Here are two approaches which we developed. There's a genetic algorithm, a machine learning algorithm. Both involve the full information, green curve or black curve, but nevertheless, both differ, which is a very sad story, which means that both these results are not valid. Can we do better? And the solution which we found was we can get additional information if we try to represent this dynamic structure factor in a different way via the density response function. So this is standard liquid theory or correlated plasma theory. The Vlasov type quantum plasma quantum Vlasov approximation is called the random phase approximation, which follows if this G is 0, then this is just chi 0. And the correlations are sitting here in this function G. And for this G, we know a number of additional properties. And we build in these additional properties in order to get more information when we compute this, when we sample this in the Monte Carlo procedure, to build in more information into this S. And the result which comes out is the blue curve. And this blue curve is, of course, much better and it's accurate, and we can get it converged with long simulations. And again, it shows that these previous simulations with insufficient information are not good enough. So this is the RPA, the red curve, and the curve which contains correlations or collision effects is typically shifted to, has a blue shift to lower frequency, and it's broadened. So now that the simulations work, we can generate data for the dynamic structure factor. This is shown here. And here we have the frequency dependence. Here we have different wave numbers, and we compare RPA to this quantum Monte Carlo results. Again, the blue curves are shifted to the left. There's a difference at intermediate wave numbers. So this is just a moderately coupled system, RS equals 2. And the differences grow if we increase this RS, then the correlations coupling increases. Here you see a stronger shift, and here at RS10, which is below metallic densities, the shift is quite high. And if you look at the plasmon dispersion, here's the plasma frequency. The interesting thing, what you observe here is that RPA has this typical monotonic increase. This quantum Monte Carlo peak position, so this is what I plot here, the peak position has a decreasing range at intermediate Q. But we have to be careful in calling this a negative dispersion, as we have seen in the talk of Sergei Rapak today for classical plasmas. This is of course possible, but before one calls the peak position of the dynamic structure factor, which shows such a behavior, a negative dispersion, one has to ask, how do we compute the plasmon dispersion? So this requires the dielectric function. And here, this dynamic structure factor contains the imaginary part of the inverse dielectric function. This is not the dielectric function, so the behavior can be different. So for this reason, I have here one slide about dielectric functions for warm dense matter. So what we need is finite temperatures, quantum and correlation effects. Here is the quantum Vlasov dielectric function, which I called RPA, which probably most of you have seen. This is a polarization function with the distribution functions. It depends on temperature. This is a retarded function. So this is a positive infinitesimal quantity. And the full dielectric function is given here. So if you want to include correlations, again, we have this G appearing here, and you replace this pi in this formula by this pi. And since we now can compute accurate dynamic local field corrections, we can also compute accurate dielectric functions. And this is what we did. And the results are given in these, this paper 4, for example, and you can read it on arXiv. So about the plasmon dispersions. Most of you will have seen these dispersions. For example, in units of the plasma frequency, we have the Bohm-Gross dispersion, which goes quadratic in Q with a thermal velocity. For quantum plasmas at 0 temperature, Bohms and Pines got the quantum result, which also has a quadratic term, but going with a Fermi velocity. And they already computed the quartic term in Q. The best result for a long time was due to Farrell, who improved this quartic term. He got this additional term, which involves the fluctuation of the velocity at 0 temperature. So this is this term given here. Quantum hydrodynamics of Manfredi and others got the wrong dispersion here. They have the factor 1/3 instead of 3/5 for 3D plasmas. They corrected this then by modifying the pressure, but this is of course not consistent. And quantum hydrodynamic in this version has more problems, which I pointed out in last year's paper. We plotted, or we computed an improved version of this Farrell function for finite temperature. And the formula is very similar. Now we have the second moment to be computed with a Fermi function. You have the deviations or the fluctuations of the fourth moment, so to say, and this is the exact result up to the fourth order. This can be parameterized for arbitrary plasma warmth beta parameters, which is also in this paper. So how do these curves look like? Here's a typical picture of the dielectric function. And here how you compute it. Normally you solve Maxwell's equations. This is the dispersion relation. We only look at longitudinal modes, so you find zeros of the dielectric function. Typically you assume weak damping. This means you just look for zeros of the real part of the dielectric function. This is shown here. The real part is a blue curve. So, and here it crosses 0, and here it crosses 0, and the second is typically associated with the plasmon. This is imaginary part of inverse dielectric function, which is related to the dynamic structure factor. So both appear at very close positions, but not exactly. This is a small wave number. Now at a larger, slightly larger wave number, you see that the blue curve has no zeros at all. So these zeros vanish at a finite Q, so there's a critical Q. So does it mean that we don't have plasmons in this case? It does not, of course, because here in this case, the imaginary part, the orange curve, is quite broad. This means strong damping. And if strong damping is observed, of course, the weak damping approximation fails. What you then have to do is to remind yourself that this dielectric function is a complex function. And essentially you have to find complex roots, and the dispersion relation means you have to solve for the zeros of the real part and of the imaginary part simultaneously. So this is shown here. Just look at the lower right figure. Here we plot the imaginary part of the frequency. Here is the real part on this axis. The dotted line are the zeros of the imaginary part, and the full lines are the zeros of the real part. So this is the RPA, and this is a correlated result. And the crossings, which is shown by the arrows, give you the correct plasmon dispersion. And as it turns out, these zeros exist much longer. This is shown here. Here is wave number Q for RS1. And this is a weak damping result. It's a blue curve here. It goes away. This is an improved weak damping approximation, and the full complex result is this thing. This exists much longer, and this is the correct result. Yeah? Of course, it's more complicated to calculate. So here is another picture. This is very busy, only to show you that one has to be very careful with these approximations. The gray area is the part which is called pair continuum, where plasmons will be highly damped. The full lines here are the solutions of the complex dispersion relation which I showed, and these green curves, these are the various approximations which I showed at the first slide. So the best approximation with these fourth order velocity moments are the dotted lines. This is the next approximation, and this dashed dotted green line, this is if one neglects all the quartic terms in the dispersion relation. So it is very difficult to get some, let's say, tendencies out of here. So just if I go to higher temperatures, one sees even larger deviations of these analytical results. So the best strategy to do is to really solve for the complex zeros of the dielectric function within the approximations which you use. Another point one has to make, we can now compare the solutions of the dispersion relation. So the full
We have
line is
3 more minutes to go.
okay, I'm almost finished. This is a solution of the dispersion relation, and the red curve is the peak of the dynamic structure factor. And we have seen that the peak of the dynamic structure factor has this tendency to have a minimum. The dispersion relation has not. So one has to be careful in interpreting the peak of the dynamic structure factor as plasmons. You always have to compute both the structure factor and the dispersion relation. So this is shown here, but I will skip this and I come to my summary. I've advertised to do accurate quantum Monte Carlo simulations in order to describe this complete system, which is a quantum plasma or warm dense matter. With this, one can compute accurate thermodynamic quantities, which are input for all kinds of metals, models, including density functional theory, using simulations for the inhomogeneous electron gas. One can parameterize the important correlation quantity, the local field correction. And also I showed in the second part results for dynamic quantities like the dynamic structure factor and for the plasma dispersion, which we can get for the electron gas from these simulations without approximations. So this allows to directly compare to the best experiments at the moment, Thomson scattering. And one word about quantum hydrodynamics. It can be derived in a much more rigorous way as in the original versions, but it turns out that many coefficients in these equations depend on the frequency, depend on the wave number. So you cannot use a universal version of the QHD. You also always have to be careful for what applications, for what modes you want to apply QHD. Nevertheless, it's a strong method if it's used appropriately. And finally, I did not talk about time-dependent problems. Here one can use quantum kinetic theory, non-equilibrium green functions, and this allows to do a lot of, let's say, transient phenomena, but of course it is a challenge to do. With this, I thank you for your attention.
So we are having two or three questions. Uh, the one question is from Mr. Sunil Sharma. What is the significance of WDA?
Significance of W what?
WDA. The question is in the chat. You can see there.
In the chat for WB.
It may be WDM. WDM, I think.
Okay, weak damping approximation. This was my shortcut. So typically you solve not the complex dispersion relation, but you just look for zeros of the real part of epsilon, right? But this is an approximation. And what I presented here were some tests, and I showed that for many situations, this approximation fails, especially for large Q, it fails. So the significance for small q is always good, but nobody knows beforehand for what is the limiting q where it works. And even if you compute the damping, the imaginary part of the frequency, we found that this approximation can even fail then when this damping is still small. Yeah, it's not necessarily, it's not sufficient criterion. Huh?
And there's another question from Rosina. How to incorporate magnetic field quantization in warm dense matter in kinetic theory?
Very good question. So magnetic field quantization can be incorporated if you treat the magnetic field quantum mechanically. So you go to quantum electrodynamics and treat it via quantized vector potential and static potential. So if you look in my book, Quantum Kinetic Theory, there is an explanation of that. But it's, of course, very cumbersome, one has to say. And one really has to think when it is important. So let's say if you look at high intensity electromagnetic fields, quantization effects probably will not be the dominating effects. Then a classical treatment of the field is probably good. At low density, low intensity, which is, let's say, especially for, let's say, single photon experiments, then of course you need a quantum treatment.
There's one more question from Vikrant Saxena. Could you please comment on computational requirements for QMC?
Good point. The requirements depend, let's say, on the size of the system. The plots which I showed were finite system calculations like 30 particles, 60 particles, but this is not critical. We found extrapolations to the thermodynamic limit. So the requirements for these quantum Monte Carlo simulations are we typically run the calculations on a compute cluster, and simulation time can be from 1 hour to several days. So, but the good thing for quantum Monte Carlo is it is highly parallelizable, so you can run it independent runs on several machines. So I would say it can not only be done on huge machines, you can also do a lot of useful calculations on your PC.
Rosina wants to ask some question directly. Can she ask? Rosina, can you unmute your mic and ask?
I cannot hear anything.
Cannot hear me.
Your voice is not coming properly, Rosina.
Maybe you type it.
My mic is on. Can you hear me now?
Please.
A little bit, yes.
Okay. I'm Regina Chaudhary from Pakistan.
Voice is not clear. I think you should now stop the talk.
Okay.
Later you can write to Professor Bonich. He will clear your all queries.
Sorry, I couldn't hear.
We don't have any more questions in the chat now. So we should thank the speaker now.